Okay, so this is my second try at this video. Hopefully my voice won't give out. Um, so in this video I'm going to prove that there are exactly 5 regular polyhedrons. So a regular polyhedron, you'll recall, is a faceted shape, so you can think of a 3D shape like a dice, with all faces the same and all vertices the same. So all faces have the same shape. And all the vertices are the same. Or another way to think of it is each vertex is kind of looks the same if you look at it. So the same number of faces meet at each vertex, and each face has the same number of edges. So for example, in a square here, each face, ooh, I like that rainbow colored pen. Each face has 4 edges. And if you look at the vertex, 3 faces meet at each vertex. Actually, I kind of hate that colored pen, but I'm going to stick with it. So notice a cube has that. So each face is the same. Each vertex is the same, and you can probably list, or I did in class the other day. I listed all the possibilities here, but it's surprising that there are only 5 platonic, only 5 solids, 5 regular polyhedra that in existence. You can't make any more, and this is an old fact. This was known to the Greeks. In fact, the Euclid's Elements, the conclusion of Euclid's Elements, like the highest thing you learn out of Euclid's Elements, is that there are exactly 5 regular polyhedron. So to do this proof, there are many proofs of this fact, by the way, and I would encourage you to Google this and find some proofs of this. But to use Euler's formula to prove this fact, the first thing you have to do is get some relationship between regular polyhedra and planar graphs. So there is a one-to-one correspondence between planar graphs and polyhedra in general. So this is not regular polyhedra, limited to regular polyhedra, but any polyhedron, any faceted 3D shape in space can be represented by a planar graph. So we are actually going to prove a fact about planar graphs that's equivalent to proving that there are exactly 5 regular polyhedra. So the theorem we're going to prove is there are exactly 5 regular polyhedra. And it was certainly known to Euclid. Often it's credited to Euclid, but it was also known prior to him. And I don't know who the actual first mathematician to look at this was. So the proof. So it's enough to show, actually, that there are only 5 planar graphs that meet certain characteristics. One is that each of the faces has the same number of edges, and that all the vertices have the same degree. So remember, the degree of a vertex, if you have a vertex, is the number of edges coming out of that vertex. So this one, for example, has degree 4. Showing something as the graph associated to a regular polyhedra is going to have all faces having the same number of edges and all vertices having the same degree. And there's another restriction. This is a little subtler, is that if this is going to be a graph that represents a polyhedra, each of the vertices has to have degree at least 3, and you can consider something trying to enclose space. If one of the corners had degree only 2, it would have only 2 edges coming from it, so it couldn't sort of enclose space. And you can think about the corner of a cube, right? It has 3 edges coming from it, because it has to sort of branch out to enclose space. And then all of the faces have to have at least 3 edges, and you can that's easy to see why that's true. You can't have a 2-edged face. Right? There's a 2-edged face. You need a 3rd edge to enclose a face. And actually the simplest one that has this there is a tetrahedron. And it would have a face and a line in the back. So there's another regular polyhedron. So let's get some notation. We're going to let d be the degree of the vertices. Remember, that'll be the same for all the vertices on our graph, and we'll just call it d. And let k be the number of edges for each face. And what do we know? We know d is greater than or equal to 3, and k is greater than or equal to 3. And we've seen, right, if you look at the, if you consider how these work, if I multiply the number of vertices times the number of edges coming out of that vertice, that's the degree. So the number of vertices times the degree, that'll give you twice the edges. And if you think about it on a cube has what, 1, 2, 3, 4, 5, 6, 7, 8 vertices, each of degree 3. So if d is equal to 3 and the number of vertices is equal to 8, that should be equal to twice the edges. And if we count the edges, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. And that, of course, is true. The other thing we saw in class the other day is that if we take the number of edges on each face times the number of faces, that'll also give us twice the number of edges. And so if you think through this, each face has, on a cube, each face has 4 edges, so k is 4. How many faces are there? There's 6 faces, so 4 times 6 is 24, which should be twice the number of edges, which you've already counted as 12. Well, yeah, that's true. And let me go ahead and say where I got these from. That's d, that's v, and that's twice the edges. And this is k, and that's f, and that's twice the number of edges. So that's just an example, of course. Now, we know that a planar graph has to satisfy vertices minus edges plus faces is equal to 2. So let's substitute these two relationships we have into this formula. And what we'll get is, we'll get this thing if you do the substitution. And now if I multiply everything in here, if I multiply this whole equation by 1 over 2e, I get this relationship here. And then if I just move the 1/2 over to the other side, I get 1 over d plus 1 over k is equal to 1 over e. Now there are some consequences of this. So notice that d and k can't both be greater than 4. So d and k can't both be greater than 4, because if d and k were both 4, then this side would be 1/4 plus 1/4, or something smaller than a fourth, which would be less than 1/2 plus anything, right? And e is supposed to be a positive number. So d and k can't both be greater than 4. Even I can't see my little pen thing. So, so 1 of d and k is actually equal to 3. and the other is some integer that is at least 3. So 1 of d or k is 3. The other is greater than or equal to 3. So let's just try the ones that work. So set d equal to 3. This rainbow color is kind of annoying, but I can't change it the way I've got the screen set. Then we get 1/3 just from the equation above. We get 1/3 plus 1 over k is equal to 1 over e plus 1/2. So 1 over k is equal to 1 over e plus 1/6. And since 1 over e is positive, this means k can't be any larger than 5. So k can't be larger than 5. And you can see why that is by just trying some numbers. If you can't see why that is, you should try some values in there. So so d is not larger than 5. And similarly, just by symmetry actually, if k is equal to 3, then, oops, I'm sorry, I meant to say k here. K is not larger than 5. We've already got d is equal to 3. That makes no sense. If k is equal to 3, then d is not larger than 5. And so what we do here is this leaves only 5 possibilities. This leaves only 5 possibilities for d and k. Since d and k both have to be integers, and we've limited their possible values. And let me write it like ordered pairs. So this leaves only 5 possibilities for d, k, and they are, well, there's 3, 3, so both d and k could be 3. There's 3, 4. There's 3, 5. There's 4, 3. And 5, 3. And then if you use those values, 1, 2, 3, 4, 5, in this equation to find the edges and the faces that work, right? Once you know d and k, you can actually find the vertices, edges, and faces from this set of equations we have. And you'll find the vertices, edges, and faces for a tetrahedron, a cube, an octahedron, a dodecahedron, and an icosahedron, which is the 5 Platonic solids. So I realize this is a slightly different proof than the one in the book, but I thought it would be fun to see a different proof. And I think I'll leave it at that. I will try and make one more video if I can, but again, my voice is giving out.